What if one of the most famous unsolved problems in all of mathematics isn't just, an intellectual puzzle,
Yeah.
not just this tantalizing enigma waiting for some brilliant mind to finally crack it? What if it's actually something more, like a powerful force, almost alive, shaping an entire field?
Directing careers, even defining what counts as truth within mathematics itself.
Exactly. It's a
Yeah.
truly captivating notion, isn't it? Now, many of you listening today, especially if you follow topics where science, philosophy, and these huge intellectual challenges meet, you've undoubtedly heard the name, the Riemann hypothesis.
Oh, absolutely. It's legendary.
It really is. It's like this mathematical Mount Everest. It's captured the imagination for generations, even if the deep mathematical details are pretty specialized.
Very specialized,
So
yes.
today we're taking this abstract conjecture, this cornerstone of modern number theory, and we're going to look at it through a really surprising and I think illuminating lens.
We're bringing in Foucault.
We are. We're going to apply the philosophical framework of Michel Foucault, specifically his idea of power knowledge.
Mm.
And we're going to use that to understand the Riemann hypothesis, not as just a static problem on a page, but as like a dynamic engine of influence.
A machine, almost.
Yeah, exactly. So our core question for this deep dive, framing it in Foucaultian terms, isn't how do we solve the Riemann hypothesis? We're definitely not trying to prove or disprove it here.
No, that's way above our pay grade today.
Right. Instead, we're asking, what does the Riemann hypothesis do? How does it actually function as a form of power and knowledge within the intricate world of mathematics?
So focusing on its effects, its role.
Precisely. It's not about the numbers themselves or the elegant equations deep inside it, but about the social dynamics, the intellectual structures, the institutional forces it creates and maintains. And our insights today, they're drawn from some deep analysis, looking at critical perspectives like those in texts exploring this very connection, such as the Foucaultian Riemann hypothesis, power and knowledge in mathematics.
It's a fascinating intersection to explore.
It really is. But before we dive headfirst into Foucault's framework, maybe we should establish some common ground on the enigma itself.
Good idea. A quick primer.
Yeah, because while many of you listening are probably familiar with its significance, just for context, and to really appreciate the sheer weight it carries, let's just briefly touch on what the Riemann hypothesis actually is.
Okay, yeah, that's an excellent starting point because even without getting lost in the deep complexities of analytic number theory, just grasping its essence is pretty crucial for what we're discussing. So the Riemann hypothesis, or RH as people often call it, was put forward by the brilliant German mathematician Bernhard Riemann.
Back in the 19th century, right?
That's right, 1859, in this really pivotal paper on the number of primes less than a given magnitude. And at its heart, it makes a very precise claim. It's about the behavior of a specific mathematical function, something called the Riemann zeta function.
Okay, the zeta function.
Yeah, and specifically, it's about where this function equals zero, its zeros, particularly what are called the non-trivial zeros.
Non-trivial zeros. Sounds important.
They are. The hypothesis claims these specific zeros all lie on a very particular line in the complex plane. It's called the critical line.
Okay, so it's a statement about the locations of these special zeros. But why does that matter so much?
Well, that's the amazing part. This zeta function, even though it sounds incredibly abstract, is actually deeply, intimately connected to something very concrete and fundamental, the distribution of prime numbers.
Ah, okay. Primes.
Yeah,
Like 2, 3, 5, 7. The basic building blocks.
exactly. Those indivisible numbers that form the foundation of arithmetic. If you could precisely understand where the zeta function hits zero, especially these non-trivial zeros along that critical line, you would essentially unlock the deepest secrets of how prime numbers are scattered along the number line.
Wow. So it's not just counting them, it's about their pattern, or lack thereof.
It's about their pattern, their inherent randomness, but also the underlying order. Understanding this distribution isn't just a pure math curiosity either. It has implications that ripple outwards.
Like where?
Well, areas like modern cryptography rely heavily on the properties of large prime numbers, so understanding their distribution is fundamentally important there.
Right, for secure communication and things like that.
Precisely. And even in theoretical physics, believe it or not, connections have been found between the spacing of these zeta function zeros and energy levels in certain quantum chaotic systems. It's quite remarkable.
So it's definitely not just some obscure mathematical footnote. It's a key to understanding the very fabric of numbers and, yeah, by extension, significant parts of our digital world and even physical reality.
That's a good way to put it. It holds a really central position.
And the challenge, as you hinted, isn't just its complexity, but the fact that it's remained unsolved for so long.
Yeah.
That persistence.
Exactly. And that persistence, that elusiveness is precisely what makes it such a potent subject for our Foucaultian analysis today. It has, as you said, famously resisted all attempts at proof or disproof for over 160 years now.
Just think about that. Over a century and a half.
Yeah, just pause and consider the sheer intellectual gravity of that. Generations upon generations of the most brilliant mathematical minds, figures like Hadamard and de la Vallée-Poussin back in the late 19th century who made huge strides in prime number theory, partly inspired by this. Right up to today's leading mathematicians, Fields medalists, they've all grappled with this single statement.
And dedicated huge chunks of their lives to it.
Absolutely. They've developed entirely new mathematical tools. Whole new branches of mathematics have sort of blossomed in its shadow, you could say. They've devoted entire careers to chipping away at it, yet it remains unyielding.
Still standing.
Still standing. And this longevity, this persistent elusiveness, is absolutely central to the kind of power it wields, the kind of influence we're talking about today. It's not merely a difficult problem. It's become this monumental, enduring question.
Legend in its own right.
Almost, yeah. It's captivated, frustrated, and driven mathematicians for, well, over a century and a half. It's almost like a character in the ongoing story of mathematics itself.
It's truly mind-bending when you frame it like that. How a single unproven mathematical statement can hold such incredible sway. Like an intellectual lodestar, dictating where a significant chunk of an entire field focuses its energy. It just stands there, this unbreached fortress, yet it commands legions of researchers. It's fascinating. Now, to really get under the skin of why and how it exercises this influence, we need to bring in that philosophical lens we mentioned.
Foucault's power knowledge.
Right. Let's delve into Foucault's framework. Now, for those maybe less familiar with Foucault, this might initially seem like a bit of a leap, right? Connecting dense French philosophy with abstract mathematics.
It can seem like mixing oil and water at first glance.
Yeah. But bear with us,
Yeah.
because this is where the really unexpected and I think powerful connections start to emerge. How does Foucault help us understand the RH?
Well, this is where the analysis really starts to take shape. For Foucault, the concept of power knowledge is pretty revolutionary because it challenges a very common, almost intuitive assumption we have about knowledge.
Yes.
The assumption that knowledge is simply about objective truth, something pure, untainted, discovered independently of human systems and biases.
Just finding facts about the world.
Right. Foucault argues that this isn't really the full picture. Instead, he suggests that knowledge is deeply, inextricably intertwined with power. It's not separable.
Okay, so knowledge and power are linked. How?
He argues it's not just about what is true in some universal, disembodied sense. It's more about the systems, the discourses, the ways of talking and thinking, the institutions, and the practices that produce what we come to accept as truth.
Ah, so it's about what gets validated as truth.
Exactly. Within a given time in history, within a specific domain like medicine or law or even mathematics, these systems, these established ways of thinking and speaking, they actually define the very boundaries of what can even be considered knowable, rational, or valid in the first place.
So they set the rules of the game for what counts as knowledge.
Precisely. And crucially, Foucault clarifies that power isn't solely about oppression or saying no or just limiting what you can't do. That's often how we think of power, right? As restrictive.
Yeah, like rules, censorship, control.
Right. But Foucault's really provocative insight is that power is fundamentally productive.
Productive? How so?
Power actively generates things. It creates entire fields of study disciplines like psychology, criminology, certain ways of practicing medicine. It does this by defining their objects of study, like the criminal or mental illness, and their acceptable methods.
Okay, so it creates the subjects we study.
And it shapes identities, too. It defines what it means to be sane or insane, healthy or diseased, normal or deviant. These categories aren't just natural. They're often produced by these power knowledge systems.
I see. And for our discussion?
Critically for today, it even defines what constitutes reality or validity within a given intellectual domain. What we think of as real or true in science or math is often, Foucault would argue, a product of these specific power knowledge systems.
Wow, that's a big claim.
It is. What's fascinating here is that Foucault challenges us to look beyond the surface claims of objectivity. He wants us to see how these underlying structures, the way questions are framed, the methods deemed acceptable, the institutions that hold sway actually dictate what counts as valid knowledge.
And how certain ideas gain authority while others are dismissed.
Exactly. How entire intellectual landscapes are constructed. He encourages us to ask critical questions like, who benefits from this particular definition of truth? And what does this truth do? What does it enable? What actions, what research paths does it open up? And just as importantly, what does it exclude or push to the margins?
That distinction about power being productive, not just limiting, is really key, isn't it? It's not just about starving things. It's about making things happen.
Absolutely.
Your analogy earlier about the rules of a sport is helpful. The rules aren't just there to say, don't do this. They actually create the game. They define what a goal is, what an offside is, what counts as a win. Without those rules, the specific game just doesn't exist in a recognizable form.
That's a perfect analogy.
So Foucault's kind of saying that these power structures create the very definitions and rules of engagement within which knowledge operates. They set the terms. Okay, so let's make the connection. What does all this mean for a seemingly super abstract mathematical problem, like the Riemann hypothesis? It feels so far removed from the usual social structures Foucault analyzed, like prisons or clinics.
Right. It seems purely intellectual.
Yeah. So how do we translate this philosophical lens to the world of prime numbers and zeta functions? Because this is where it gets really, really interesting.
Absolutely. Let's start with this idea. The Riemann hypothesis acting as what Foucault might call a regime of truth within mathematics.
A regime of truth. Okay, what does that mean in this context?
Think of it this way. Every field, every scientific discipline, every intellectual pursuit, it has its guiding stars, right? Its maybe unassailable foundational principles, or perhaps its most significant defining challenges.
The big questions everyone agrees are important.
Exactly. And the RH occupies that kind of paramount position in large segments of modern mathematics, especially in number theory. It effectively sets the gold standard. It's a benchmark for what's considered significant, cutting edge, and crucially valid research.
So working on or near the RH gives your work instant significance.
To a large extent, yes. And its immense status, this isn't just some accidental cosmic alignment. It wasn't predetermined that this had to be the biggest problem. It wasn't purely an objective measure of difficulty alone, although it is incredibly difficult.
Yeah.
It has been meticulously built up and maintained by the mathematical community itself. This community, through its conferences, its leading journals, the very structure of its graduate education, its prizes, often implicitly, sometimes explicitly, collectively decided this is the problem to solve.
A consensus was formed around its importance.
A very powerful consensus. And this shared belief in its paramount importance is, in itself, a powerful collective act. It shapes what is deemed worthy of pursuit, what gets funding, what young mathematicians are encouraged to work on.
Okay, so the community elevates it. And how does that give it power?
Well, this status, this almost sacred position it holds, gives the RH immense power to validate other knowledge.
Validate. How so?
We see this most clearly in what the source material we looked at aptly calls the vast castle of conditional knowledge.
Conditional knowledge, meaning?
Meaning hundreds, maybe even thousands, of mathematical theorems and proofs are built on the premise. If the Riemann hypothesis is true, then this other thing we've proven is also true.
Ah, so their truth depends on the RH being true.
Exactly. They are proven, but conditionally. Think about, say, the famous Goldbach conjecture. The idea that every even integer greater than 2 is the sum of 2 primes. Still unproven.
Right, another famous one.
Well, some of the most significant progress on related problems, like the odd Goldbach problem proving that every odd integer greater than 5 is the sum of 3 primes, which was proven conditionally first by Vinogradov and then essentially fully by Helfgott, relied heavily on assuming the truth of variants of the Riemann hypothesis, specifically the generalized Riemann hypothesis.
Wow. So major results hang in this conditional state.
Yes. And this isn't just some abstract theoretical link. It dictates the very landscape of how proofs are constructed and presented in number theory. Mathematicians literally publish papers saying, assuming GRH, we prove X.
So they're effectively saying, look, we've done the work, we've built this structure, we can prove X, Y, and Z provided the RH holds. It creates this really peculiar kind of fascinating situation within math, doesn't it?
It really does.
You have this massive edifice of mathematical understanding, entire areas of research, all sort of waiting for this single, unproven king's decree, the proof of the RH to make them entirely real or, fully confirmed.
It's like building a magnificent skyscraper, but leaving the central pillar made of, say, incredibly strong, but still technically unverified material.
Yeah, like a sprawling city built on these incredibly strong but technically temporary foundations. Everyone believes they'll hold, but they're all waiting for that final colossal keystone, the proof to be definitively slotted into place.
And the provisional nature, as you say, it doesn't invalidate the work itself. The logic within those conditional proofs is rigorous, but it certainly shapes the meaning and the future status of that work.
It forces mathematicians to categorize their results carefully. You see paper titles like Conditional Results on the Riemann Hypothesis all the time.
All the time. And the possibility, however remote mathematicians might currently feel it, is that the RH could actually be false.
Huh.
Well, that would send seismic shockwaves through huge segments of number theory.
It would force a massive reevaluation.
A reevaluation of vast amounts of work. It's almost like this speculative architecture of knowledge built on a foundation everyone trusts, but no one has definitively proven is bedrock.
It makes you wonder, doesn't it? Thinking about what you said earlier, this raises that interesting question. How many other fields, scientific or otherwise, rely on these kinds of unproven pillars?
Exactly. Foundational assumptions that are widely accepted, incredibly fruitful, they generate tons of research, but still await that definitive proof.
It really shows how even in the most rigorous disciplines like mathematics, there's still this element of, maybe not faith exactly, but collective agreement, shared belief that underpins vast areas of understanding.
And the very act of this collective waiting, this shared anticipation for the proof, the structure of conditional results, that itself gives the RH its power. It becomes the focal point.
Yeah. It's a testament to the idea that even something unproven can hold immense sway simply by being designated the problem. It shapes inquiry. It validates whole subfields.
It organizes the field.
That's a profound thought. And this leads us perfectly into our next point, which really builds on that Foucaultian idea of power being productive.
Not just restrictive.
Right. The Riemann hypothesis isn't just this static problem that sits there passively waiting to be solved. It's an incredibly productive engine. It actively generates things. It's not just a wall, it's a dynamo.
Absolutely. That's a fantastic way to put it. The RH functions as this massive, almost self-sustaining research engine within mathematics.
Now, so, what does it produce?
Well, think about its outputs. Tangible things. It generates countless international conferences. Often you'll find entire sessions or even whole conferences dedicated solely to advances related to the Riemann hypothesis or the zeta function and its cousins.
So it creates meeting places, hubs for ideas.
Exactly. Vibrant intellectual hubs where the latest ideas are exchanged, potential breakthroughs are announced, collaborations are formed, and frankly, careers are made or boosted.
And it fuels careers directly.
Oh, definitely. Many mathematicians dedicate decades of their professional lives to its pursuit or to problems deeply connected to it. They build a significant body of work around its various facets, the theory of the zeros, the distribution of primes, computational aspects. For some, the RH becomes the central defining quest of their entire academic lives.
Wow. Decades on one problem.
And it produces publications. Volumes upon volumes of papers published in the most prestigious mathematical journals. These papers constantly push the boundaries of analytic number theory, computational number theory, algebraic geometry, even connecting to areas of physics, as we mentioned.
So it drives innovation across multiple areas.
Hugely. It quite literally spawns entire subfields of mathematics that arguably wouldn't exist or certainly wouldn't be as prominent or well-developed without the gravitational pull of the RH.
Can you give an example?
Sure. Think about the theory of L functions. These are generalizations of the Riemann zeta function, and the study of their properties, their zeros, their connections to other mathematical objects. A lot of that intense activity is directly spurred by the hope that understanding these more general functions might shed light back on the original RH.
So it casts a long shadow.
A very long, very productive shadow. Or consider computational number theory. There's been incredible innovation in developing highly sophisticated algorithms and using massive computing power just to search for zeros of the zeta function further and further up the critical line, verifying the hypothesis for trillions of zeros.
Just to check it, essentially.
To check it, yes, but also hoping to find a counterexample or perhaps gain some statistical insight into the behavior of the zeros. All driven by this one central problem.
It's really amazing. So this isn't just about individual mathematicians being curious, although that's part of it. The RH itself provides this overarching structure.
It provides an organizing principle, A monumental, maybe the monumental career-defining goal for many in the field. It effectively structures their lives and their work. It gives them a clear focal point for their intellectual energies, their collaborations, and yes, even their competitive drive. It channels effort.
I can almost picture it now. The buzz at a major math conference when someone presents a new result, even a small one, that seems to indicate closer to the R age or opens a new angle.
Oh, the excitement would be palpable.
Yeah, the excitement, the intense scrutiny from the experts, the collaborative energy it sparks, it must be incredible. It really speaks to how these grand challenges, like the RH, mobilize resources, attract the brightest talent, and fundamentally shape career paths. They define what progress even looks like within that field.
It truly is like a perpetual motion machine of intellectual effort, constantly churning out new mathematics.
But, as Foucault always reminds us, this productive power, this generation of knowledge and activity, it isn't just about creating freely. It also implicitly, sometimes explicitly, creates boundaries. It enforces discipline.
That's the other side of the coin.
Right. And this leads us to thinking about how the RH actually helps create specific identities within the mathematical community that revolves around it.
This is a crucial and sometimes, let's be honest, slightly uncomfortable aspect of how power knowledge operates. The creation and delineation of roles and identities. It establishes who's in and who's out.
Okay, so what kind of identities emerge around the RH?
Well, within the mathematical community focused on the Riemann hypothesis, there's often a fairly clear hierarchy, a defined set of roles that people recognize. On one hand, you have the RH expert.
The authority figure.
Pretty much. And this isn't just someone who knows a lot about it. They are seen as the undisputed authority, often acting as a kind of gatekeeper. Their function is to understand the deep theory, the intricate history of attempts, the vast web of conditional knowledge we talked about, and the established, accepted methodologies for tackling the problem.
So they know the landscape inside out.
Exactly. And because of that, they validate what counts as a serious, legitimate approach to the problem. Their endorsement, or perhaps more powerfully, their critique, often delivered in peer review for journals or in pointed questions after a conference talk, can literally make or break a new line of inquiry or a claimed breakthrough.
Wow, that's a lot of influence.
It is. They are, in a sense, the guardians of the established discourse around the RH. They maintain the standards.
Okay, so that's the expert. What's the flip side?
Well, then, on the other end of the spectrum, you often find what's sometimes colloquially, perhaps unkindly, termed the crank.
Okay. The outsider.
Often, yes. This might be an amateur mathematician, someone working outside the mainstream academic system, or even an established mathematician whose proposed approach simply falls too far outside the accepted paradigms, the established ways of thinking about the problem.
And how are their attempts treated?
Typically, their attempts, which often come in the form of grand claims of a full proof, are swiftly and decisively dismissed by the expert community.
Dismissed outright.
Frequently, yes. And it's important to try and understand why from a Foucaultian perspective. This dismissal isn't necessarily rooted in personal meanness, though I'm sure it can feel incredibly harsh and invalidating to the individual involved.
Right. It must be crushing.
Absolutely. But from the community's perspective, this act of dismissal is how it exercises power to maintain the integrity and the established rules of its discourse. It's a way to protect the field, as they see it, from what they consider non-rigorous, fundamentally misguided, or simply time-wasting efforts.
So it's a defense mechanism for the field standards.
It functions as a form of academic and intellectual discipline. By defining who is a legitimate expert, who speaks the correct mathematical language, who uses the accepted tools, and conversely, who is a crank, pursuing a dead end, the community actively shapes who is allowed to contribute meaningfully.
It determines whose ideas are taken seriously and whose are essentially ignored or relegated to the fringes.
Precisely. It defines the very boundaries of what constitutes legitimate mathematical practice within this specific high-stakes domain. It ensures, or aims to ensure, that the collective effort remains focused and adheres to extremely high established standards of rigor.
It really is like that invisible bouncer at the mathematical club door, isn't it? Checking IDs, making sure only those who understand the secret handshake, the deep theory, the established methods, the accepted jargon, get in and get heard.
That's a good analogy, and it captures some of the dynamic.
And this process, as you say, isn't necessarily about being intentionally unkind. It's fundamentally about maintaining the perceived integrity of the field. And in doing so, it constantly redefines what serious math even means in this context.
It reinforces the norms.
It's fascinating to consider how pretty much any specialized field, really, whether it's theoretical physics or literary criticism or brain surgery, establishes its own internal hierarchies, validates expertise, and manages dissent or unconventional approaches. It's a universal dynamic, perhaps.
It seems to be. But it does raise a critical question, doesn't it?
Which is?
Is there a risk that this strict gatekeeping, this disciplinary function, while absolutely essential for ensuring rigor in a field like mathematics where subtle errors can invalidate entire proofs, might it also inadvertently stifle truly revolutionary ideas? Ideas that are initially unconventional, that don't fit the current mold, but might hold the key.
Yeah, the outsider perspective that sometimes sees things differently.
Exactly. That's a crucial tension, and one Foucault would certainly want us to keep in mind. While the discipline maintains integrity and prevents the field from being drowned in, frankly, a lot of non-rigorous claims, especially for famous problems like RH, which attract many attempts.
Right, I imagine they get flooded.
They do, but it also inherently creates potential blind spots. History is full of examples across science where ideas initially dismissed as crankery or simply ignored later turned out to be revolutionary precisely because they challenged the existing paradigm.
So it's a balancing act.
It is. Within the specific context of problems like the Riemann hypothesis, the community standards are extraordinarily high, and perhaps necessarily so, given the immense complexity and the potential for subtle, hard-to-spot errors in any purported proof. The challenge always lies in discerning genuine groundbreaking novelty from genuine error or misunderstanding.
And the expert identity, the established figures, usually hold the power in making that crucial distinction.
That's generally how it functions, yes. And this ongoing process constantly reinforces the community's shared understanding of what constitutes valid mathematical work in this area and what does not.
That makes perfect sense.
Yeah.
And this discipline, this maintenance of standards or identities, it isn't just some internal, informal process happening in the hallways of math departments, is it?
Not at all.
It's also formally backed up, reinforced by actual institutions. Beyond just pure intellect or individual efforts, there are tangible structures that formally support and amplify the power and status of the Riemann hypothesis, really cementing its place as a central organizing force.
Exactly right. The power of the Riemann hypothesis isn't just purely intellectual or social within the community, it's deeply institutional. It's embedded in the structures of modern mathematics.
How so? Can you give an example?
Well, the Clay Mathematics Institute, CMI, provides a prime, almost theatrical example of this institutional reinforcement.
The Millennium Prize problems.
Precisely. When the CMI, back in 2000, named the Riemann hypothesis as one of its 7 Millennium Prize problems, it wasn't merely recognizing its existing importance. That importance was already immense, well established within the field.
Right, it was already famous.
What the CMI did, more significantly from a Foucaultian perspective, was to amplify its power dramatically. By attaching that prestigious, highly publicized $1 million prize to its solution, they massively increased its visibility, its allure, and its perceived importance.
Not just within math, but to the wider world.
Absolutely, to the public, to funding agencies, to universities. This act helped transform it from being just an incredibly important academic challenge into a kind of high-stakes global quest, further solidifying its status as the problem of the age and number theory.
The prize money itself becomes this concrete symbol of its power.
It's a material manifestation of the problem's perceived value, a tangible incentive that draws attention and resources, perhaps even from places or people who might not otherwise focus on such deeply abstract mathematical pursuits. It sends a clear signal to the world. This matters profoundly, and we as an institution are willing to put a substantial sum behind its resolution.
So the institution actively elevates its status.
And this kind of institutional reinforcement extends much further, weaving into the very fabric of academic life itself.
Like within universities.
Definitely. Universities, for instance, actively factor work related to such recognized high-stakes goals like the Riemann hypothesis into their decisions about hiring and promotion.
Really? How does that work?
Well, a candidate for a faculty position, particularly in number theory or related areas, who has made significant, even if incremental, contributions towards understanding the RH or developing techniques relevant to it, perhaps through new analytical methods or major computational verifications, that candidate is often seen as a highly desirable hire.
So they're working on the big stuff.
Exactly. It signals a commitment to the field's most pressing, most prestigious challenges. It adds weight to their profile. Similarly, think about academic journals.
The top journals want papers related to it.
Immensely so. Journals gain enormous prestige by publishing genuine advances related to the RH. A paper that pushes the envelope on the theory of the zeta function, or prime distribution, even if it falls far short of a full proof, grants significant status to both the author and the journal that publishes it.
So it's woven into the whole academic ecosystem.
It's completely woven into the fabric of the mathematical establishment, from the way grant funding is often allocated, to publishing opportunities, right down to the progression of an individual mathematician's career path, their tenure prospects, their invitations to speak at major conferences.
Wow. It becomes this central pillar around which so much of the professional and institutional life of mathematicians, especially in certain fields, can revolve.
It really can. And this, again, raises that important Foucaultian question about how our institutions, universities, funding bodies, prize committees, journals, through their reward structures and recognition mechanisms, might inadvertently end up shaping the very knowledge they claim to merely house or support.
By validating and amplifying certain kinds of pursuits over others.
Precisely, by signaling what is important and rewarding work aligned with those signals.
It's a truly symbiotic relationship then, isn't it? The intellectual challenge drives the institutions to recognize it, and the institutions, by recognizing and rewarding it, reinforce and amplify the significance of that challenge, creating this powerful feedback loop.
That's a perfect description of the dynamic.
It's a fascinating look at how funding, academic structures, public recognition, they all play a vital role in shaping even the most abstract scientific and academic endeavors. It shows that even in fields that seem purely about logic and numbers, there are very real-world, organizational, and even financial forces at play, subtly directing the flow of intellectual energy and defining success.
The social and the intellectual are inseparable.
And this, I think, leads us to what is perhaps the most profound and maybe the most counterintuitive, the most ironic insight that comes out of this Foucaultian deep dive.
The paradox at the heart of it.
Yeah, the sheer power of the unproven.
Mm-hmm.
This is where the philosophical lens really challenges our conventional understanding of what makes a problem important or valuable.
This is indeed the core irony, and I think it's what makes the Foucaultian perspective so uniquely compelling when you apply it to something like the Riemann hypothesis.
Okay, lay it out for us. What's the irony?
From this viewpoint, the profound influence, the immense productive capacity we've been talking about, this entire ecosystem built around the Riemann hypothesis. It arguably depends crucially on it remaining unproven.
Depends on it staying unsolved.
Yeah.
That seems backwards.
It does seem backwards from a traditional perspective, where the goal is always the solution, the answer. But think about its function, its actual truth value, whether at the end of the day, the hypothesis is ultimately true or ultimately false, becomes almost secondary to its function as an enduring, unsolved problem.
So its role is more important than its answer.
In terms of the effects it produces within the field, arguably yes. The ongoing quest, the continuous generation of new mathematics, new techniques, new careers, all spurred by its pursuit, that is where its power, its productivity truly resides. As the source material we discussed highlights, its truth value is, in a functional sense, almost secondary to this instrumental role it plays.
Wow. Okay, so let's play that out. What if it were solved?
Right. Consider the hypothetical. Imagine tomorrow someone publishes a verified accepted proof, or equally dramatically, a verified disproof with a counterexample.
A huge mathematical moment, obviously.
A monumental achievement, no question. A proof, especially, would instantly elevate the status of all those hundreds, thousands of conditional theorems we mentioned. They'd become absolute truths overnight. A disproof would be equally earth-shattering, forcing that massive reevaluation.
But what about the engine?
That's the key question. The intense productive industry, this perpetual motion machine built around the pursuit of the proof, it might collapse, or at the very least significantly diminish.
The driving force would be gone.
The central driving force for many researchers and entire subfields would suddenly need a new raison d'etre. Careers that were built around tackling it would need to pivot. Conferences would need new central themes. The very structure that has organized so much mathematical effort for 160 years, the ongoing narrative of this epic struggle, would suddenly be resolved. The story would end.
It would lose its central pillar.
Exactly. And the sheer volume of intellectual energy, institutional capital, funding currently dedicated to attempting to solve it would need to be reallocated, redirected. The landscape would fundamentally change.
It's almost a bittersweet thought, in a weird way, isn't it? I mean, everyone wants it solved, but...
But the quest itself is so generative.
Yeah. It reminds me of those old legends, like the quest for the Holy Grail. Imagine if the Knights actually found it, or definitively proved it didn't exist. What would they do next? Would the entire enterprise of chivalry, the stories, the codes, lose its central driving force once the object of the quest was obtained or debunked?
That's a surprisingly apt analogy. The quest itself defines the questers in their world.
So, the true function of the Riemann hypothesis, viewed through this Foucaultian lens, isn't just to be a statement about prime numbers, some objective truth waiting passively to be uncovered. It's to serve as this incredible perpetual motion machine for knowledge production.
A fundamental organizing principle.
Yeah, a principle that actively shapes what mathematicians do, how they think, how they structure their research, and even who gets to be heard, who counts as an expert within the field. It's this dynamic force, and its very uncertainty, its enduring mystery, is the fuel for its engine.
Precisely. It's not merely a problem within the field of mathematics. You could argue it's a powerful agent that actively creates and sustains large parts of the very field of study it resides in.
It builds its own world around itself.
In a sense, yes, it's this self-perpetuating engine of intellectual activity. It draws in talent, it directs research funding and focus, it defines expertise, it shapes careers, and it even influences the institutional landscape of mathematics. The RH isn't just a mathematical statement, it's become this living testament to the profound power of the unanswered question.
And it shows us, maybe uncomfortably, how the pursuit of knowledge, the process, can sometimes be a far more influential force than the final knowledge itself, at least when viewed through this particular philosophical lens.
That kind of influence stemming from uncertainty and that persistent elusiveness is incredibly impactful. It drives this whole intellectual apparatus forward precisely because the ultimate answer remains just out of reach.
Wow, what an incredible journey we've taken today, really. We started with a concept that many of you listening have probably heard of, the Riemann hypothesis, this seemingly remote, purely abstract mathematical conjecture.
Something very technical.
Very technical. But we've really tried to look at it through an entirely new lens, thanks to Michel Foucault's philosophy of power and knowledge. And it just opens up such different ways of thinking about it.
It really does shift the perspective. It moves us beyond just the raw numbers, the functions, the proofs, and into thinking about the deeper structures, the dynamics that govern how knowledge is produced, validated, and organized.
And in doing that, we've seen that this deep dive wasn't really about the mathematical intricacies themselves, the zeta function or the prime numbers or the complex analysis involved.
No, not the technical details.
It was about the dynamics of knowledge and power that are constantly at play, even in math, about how an abstract conjecture can become this central organizing principle for a huge chunk of an academic discipline.
Shaping careers, generating enormous amounts of research, defining expertise.
Yeah, and defining who gets to be an expert and who gets labels a crank. It's a powerful reminder, I think, that even in fields we often think of as purely objective, like mathematics, there are always these human forces, these social and institutional forces constantly at work.
Defining what counts as truth, what counts as valid knowledge, and maybe most importantly for this discussion, what counts as important to pursue.
Absolutely.
And maybe this raises an important final question, something for you, our listener, to perhaps consider in your own world.
A takeaway thought.
Yeah, think about your own field, your own work, or even just broader societal challenges you follow. Are there foundational ideas, big questions, grand challenges in those areas that might function in a similar way?
How so?
Functioning less as absolute, settled truths or easily solvable problems, and more as these powerful engines of production and organization. Think about those elusive goals, the things that continually capture attention, funding, and effort in your world.
The things everyone talks about needing to solve.
Exactly. Could it be that they are profoundly shaping the very landscape you navigate, maybe propelling entire industries, research fields, or policy debates forward precisely because they remain unanswered or elusive, constantly inspiring that pursuit?
It's a really provocative thought, isn't it? That maybe the unsolved questions, the grand challenges, the persistent mysteries, maybe they are the truly powerful forces defining our worlds.
Propelling us forward, structuring our understanding.
Just by their enduring elusiveness. It kind of suggests that sometimes the real value isn't just in finding the destination, the final answer, but in the incredible unending journey that the question itself inspires.
The power of the quest.
It's the power of the quest. Well, thank you so much for joining us on this deep dive into the Foucaultian Riemann hypothesis. It's been fascinating.
It certainly has.
Until next time, keep digging, keep questioning, and keep exploring those incredible,